If a peer-reviewed paper published by an award-winning and respected physicist is titled Life on a Closed Timelike Curve, and, right in the introduction, it states, if such a cyclic curve forms, the spaceship returns to its own past, then for us science enthusiasts, taking this recently published paper seriously becomes inevitable. Lorenzo Gavesino, a recipient of the Merak Award, one of the most prestigious prizes in astrophysics, has shown great courage in his latest work by tackling the subject of time travel. By modeling the movement of a spaceship along closed timelike curves, he demonstrated that such a journey would not lead to paradoxes and, I quote, "The laws of nature are compatible with time travel." However, he emphasized that for the person experiencing it, the outcomes might not be what they expected. Seeing such a paper from a prize-winning physicist in a field that most physicists tend to avoid, and where even those who study it are met with skepticism, is surprising. According to the paper, time travel begins on closed timelike curves. In other words, a spaceship must be stationed on such a curve, ready to embark on its journey through time. So, what exactly is a CTC? They are theoretical structures derived from Einstein's general relativity equations. Just as Einstein predicted black holes through his equations, and we confirmed their existence within 100 years, it is not entirely impossible that we may one day discover or even create closed timelike curves. According to general relativity equations, a closed timelike curve is a loop where a person or an object, after traveling through time, can return to its starting point. You can think of it as a path for time travel, where one can go into the past and then return to the future. If you move within such a curve, past and future become interconnected, and time itself takes on a cyclic nature. How could something like this be possible? According to Einstein's general theory of relativity, under extreme gravitational forces or exotic physical conditions capable of warping space-time, closed timelike curves could theoretically form. From a general relativity perspective, the existence of such a structure seems possible. Think of it this way. Just as strong gravitational fields can slow down the passage of time, an even greater gravitational force could go beyond merely slowing time and actually reverse it. Of course, this holds true only if we do, not one day, discover a fundamental limit to gravity, just as we found a limit to the speed of light. Since no such discovery has been made yet, we continue from where we left off. While having a curve that allows for time travel theoretically, the paradoxes that arise at this point make us question whether time travel is even possible in the first place. But is this truly a theoretical issue, or is it more of a philosophical dilemma? Setting that question aside, many scientists dismiss time travel as impossible by citing paradoxes, yet they rarely delve into the mathematical foundation of the issue. This is precisely where Lorenzo Gavesino's latest paper comes into play. One of the most well-known paradoxes of time travel is as follows. If you travel back in time and kill your grandfather, how can you exist in the first place? At first glance, from the perspective of classical physics, this question seems quite straightforward. If you eliminate the source of something, that thing can no longer exist. In short, this situation completely upends the causality we have been taught since birth and presents an event that defies our intuition. However, Gavesino argues that this is not actually the case and that the standard model equations of quantum mechanics prove that paradoxes cannot arise. But let's assume for a moment that paradoxes are indeed impossible. Does that mean time travel is possible? It seems that the situation is a bit more complex than that. Now, let's imagine a spaceship entering a closed timelike curve. The passenger inside decides to travel to the past and kill his grandfather. We have no idea why he chooses to do this. He follows the time curve, travels to the past, and kills his grandfather. But then, something unexpected happens. When the traveler completes the loop and returns to the starting point, their memory is completely erased. And this is not just speculation, it is a direct statement from the paper. Lorenzo Gavesino explicitly claims that the memories of all time travelers must be erased, and the reason for this is quantum mechanics. This means that the traveler has no recollection of killing their grandfather, and everything they did effectively never happened. This is exactly what Gavesino means when he says, "I have proven that paradoxes are impossible." Of course, the scientist arrives at this conclusion using Schrödinger's equations. The paper demonstrates that the fundamental principles of quantum mechanics already ensure time consistency. The universe does not allow contradictory situations. For example, irreversible events, such as the death of the grandfather, are canceled out at the end of the time loop. The reason for this is that all systems have quantized energy levels at specific intervals, and when the loop is completed, they return to their initial states. To put it simply, time travelers are ultimately made of atoms, and for time travel to be possible, they must already be quantized. At least, this is exactly how it is described in the paper. But doesn't this mean that entropy is decreasing? In other words, even if you travel to the past and return to your starting point, wouldn't you be moving against entropy? Entropy is a measure of disorder or information loss in a system, and according to the second law of thermodynamics, it always increases. However, in this scenario, by traveling to the past, we are reaching a point where entropy has decreased. Looking at it this way, understanding what time travel really means becomes much easier. In fact, what we call time travel is essentially moving to a point where entropy has reversed one of the most fundamental rules of nature. Imagine an ice cube melting into water, but then trying to revert that water back into ice. If you're on a closed timelike curve, the ice that has already melted into water will eventually return to its original frozen state. Then it will melt again. In essence, it repeats itself in a cycle. But no matter what happens, it always returns to the initial moment. This is because a CTC necessarily contains a loop. In summary, if you travel far enough along a CTC, you return to entropy's initial state. From one perspective, this might look like moving against entropy. In the specific scenario described in this paper, entropy within a closed timelike curve can reverse. In other words, disorder can decrease. Normally, when entropy increases, a system becomes more chaotic and events become irreversible. However, within a CTC, since time is cyclical, entropy eventually reaches a peak and then begins to decrease. According to the paper, this is the exact moment when the time traveler's memory is erased. In other words, entropy resets to its initial state. Let's clarify an important point. Memory is an organized information system, and when entropy decreases, this information is lost. Aging is also an organized information system. It describes the transition of cells from a more ordered state to a more disordered one. If you're inside a cyclical entropy system, you could eventually return to your youngest state. As far as we know, CTCs are inherently cyclical. But how is this possible? According to the paper, quantum mechanics ensures self-consistency because, in a system moving along a closed timelike curve, its time evolution automatically returns to its initial state. This means that within closed timelike curves, not only space, but the entirety of space-time is forced to return to its original moment. The core argument presented in the paper is as follows. All quantum systems inside a time-traveling spaceship must inevitably return to their initial state at the end of the journey. This result is actually derived from Wigner's theorem and is consistent with the fundamental laws of quantum mechanics. That is, when a system moves within a time loop, all of its